ZFS destroys UFS by being 50 times faster in sequential writing. An insane level of performance you must see. And that is not all. ZFS dominates in random reading, beating it 5 times over using the same hardware. Stay tuned, do not miss this brutal benchmark. You can also use it on Linux distros. Its origin comes from the late OpenSolaris, which left us both SmartOS and OmniOS systems. FreeBSD includes ZFS natively and also supports UFS. ZFS is modern and fast, while UFS is classic and synchronous. We will call ZFS Z and UFS U. Now, we increase the terminal font size using bit control -F with the terminal's font set. We run df-th so it shows us the type of file system that each partition has, in addition to its total size. We start the test by writing 4 GB of sequential data with DD and FData sync, forcing the actual saving to disk at the very end. With this specific scenario, we seek to measure the sustained sequential write speed and compare the real performance of the system. We executed the test 5 times, and the average is amazing. Z obtained a write speed that was 50 times greater than that of U. After completing the write, we read the 4 GB file with DD and send the data to dev nulleo to avoid additional write operations. In this way, we measure the sustained sequential read speed and also observe how fast the system can recover data efficiently. We executed the test 5 times. Although the difference was not so drastic, Z always takes the lead with an extra 4 GB per second. Just as we measure the read and write speed, it is very important to measure the time it takes the system to delete that data completely. Z deletes the references to the file. The result is practically instantaneous, while U updates its allocation structures properly. We create a new test directory and enter it to measure how the system handles thousands of separate file creation operations now. Next, we execute a loop with 5,000 iterations using touch to evaluate metadata performance in nodes and sequential creation here. This test is very close. The difference was milliseconds to complete the task. In this case, U stands out by a few milliseconds. In the same way that we measured time in the previous test, here we also measure how long the system takes to delete the entire folder. Again, this test is very close. U also stands out by a few milliseconds. The disadvantage is that Z waits for a TXT commit. We execute a loop that calls sync 2000 times to force writing buffers and measure the total synchronization cost of the system. With time, we evaluate the overhead of repeated sync, analyzing how long it takes the kernel to flush caches to disk constantly. This test writes nothing, but Z groups writes and avoids repetitive flushes, while U forces flushes and may involve write-back. We prepared the Sysbench FileIO benchmark by creating a 4 GB dataset on disk to simulate a real file access workload effectively. This initial step generates base files used in subsequent read and write tests to measure the exact file system performance level. Although both systems are around 100 megabytes per second, Z has a slight advantage of 4 megas when compared directly with U. We run Sysbench in FileIO mode with 4 GB of data performing random reads and writes to simulate a real mixed load environment. The test measures file system performance under concurrent random access, evaluating latency and throughput in mixed operations. This is another test where Z wins by far. Even its speed is higher than the tests we have already done on Linux with ext4 and BTRFS. Again, we want to measure the time it takes the system to delete the files generated by the Sysbench test. We use the time command. The result is again shocking. Z takes practically no time, only removing references, while U still requires a few milliseconds. We use fetch to download the FreeBSD srstxz file, measuring network and storage performance under completely real conditions. This specific step allows obtaining a standard-based system dataset to use as an identical workload in ZFS vs UFS benchmark tests. We create a test directory to serve as an extraction point to measure how the file system handles massive file decompression load. With tarxf, we decompress srstxz, measuring sequential write performance and the creation of thousands of files in the system. This operation is absolutely key to evaluate metadata latency and write speed on the real workload expansion of the base system. Next, we use tarcf to repackage the files, measuring sequential reads and indirect compression of the extracted dataset here. This crucial step evaluates how the file system handles intensive reading of many small files during reconstruction of the tar file. Finally, we delete the test directory to measure massive file deletion performance and the complete release of metadata from it. This test is very important because it is real. With thousands of files and load, Z stands out in all measurements made against U. This phase allows comparing the efficiency of UFS and ZFS in recursive deletion and updating internal structures of the system. To finish on a high note, we list files. We create a snapshot of our system since I am using root, that is the actual dataset. As we see, creation was instantaneous. We use the ZFS get command to view the storage data and the exact compression ratio used. This snapshot is referencing 2.33 GB, and one of the most important features is the compression ratio nearly cut in half. We delete the two downloaded source files, check that they are gone, and looking at the snapshot data, we see they are still there. We roll back the snapshot, check the directory, and the files are there again, instantaneously. Then we see the file information. Finally, we destroy the snapshot because we will no longer use it. This was a clear demonstration of the ZFS copy-on-write feature. With these tests and demonstration, there is no doubt about the ultimate supremacy of ZFS. Performance results are truly amazing. What are you waiting for to test your system? From now on, I will use ZFS, and we did not even talk about redundancy with RAID. That is all for this video. If you liked it, subscribe, leave a like, and activate notifications. See you in the next video.